Greetings, Doctor. My name is Rami Yassin, and today I will be presenting about our assignment 2, Speed Trial 2D. So, this is our members, Yusuf Zain, Abdurrahman, Abdullah Ahmed, and Arnold Rizwan Ahmed. Now, moving on to the next slide, let's talk about what is this challenge was all about. So, in real scenario, autonomous vehicles make use of a lot of parts, which is like sensors to sense the road, to sense the environment, and detects objects. And at the same time, it make use of an decision engine to choose which decision to take, and actuators to convert the electric energy into something physical, like moving the car, braking, etc. So this is for autonomous vehicle. The challenge actually simulates this autonomous vehicle in a way that you need to apply those things, and to apply those things, you need to have uh, real-time software implemented. So in real-time software implemented, especially in autonomous vehicle, a missed deadline is a collision. So we need to have a process that works in real time without any missing deadlines. Now, for the challenge, there was three objectives are there. The first of all, collecting speed tokens. So we have three types of tokens: green token that give us extra speed, red tokens that penalize us with 20% reduction speed, and penalty, which is a yellow token, which give us a random sabotage event. And then we need to survive 4 challenges events, which are the police car, the chasing, the golden lane, and the darkness. And then we have to also maximize our distance in that challenge. Moving on, how did we implement our system in order to win this challenge? We make use of OS2 model and concurrency. So this model have a fixed priority preemptive scheduler. Basically, if there is multiple tasks that want to be run in real time and in parallel, it will prioritize the one that has highest priority and preempt the other task. And at the same time, it has a rate monotonic scheduling, which means shorter periods gets higher priority. And also all that, it have to be stand in 74.3% of RMS utilization bound for the 5 task set that we had. So this environment of the game, how do we detect this environment of the game? So we have 3 main sockets, TCP sockets. Basically, for the car, it has a front camera so that it can see the environment in front of it, and a back camera to see the back environment if there is a car coming from behind, and also controller input, which is basically how we communicate and control the car, steering it, accelerating it left and right within 150 millisecond hardware cooldown. So you cannot have movement less than that, shorter than that. So now for the game or actual tournament, it had been progressing from, first of all, during the first phase, it was basic. You just have to collect the most distance with collecting tokens. But then there's a 60%, there's challenges introduced along the way for the second phase, like chasing car, darkness, and police car. And lastly, for the tournament, there was a golden lane event, which basically allows for a lane that has no obstacles, and it's the best lane for the game. And also they increase the duration into 3 minutes. This is for the background study for our part. Now moving on to the next part.
Okay, so thank you, Rami. Good evening to all. So my name is Arnob. So since we already covered the background, so let me explain how our controller is actually structured. So the whole autonomous pipeline follows the classic real-time pattern. First of all, is like the perceive, then compute and actuate. So in the perceive stage, we take raw frames from the cameras and turn them into a structured one model. So things like where the tokens are, their lane of stress, whether a chasing car or police car is present, and the current brightness level. Then that model goes into the compute stage. So here a scoring policy looks at everything, and it decides the single best target name to move it. So it weighs the token values like green, red, yellow, also the active event stage, and as the state is so the card doesn't flip flop between lanes or goes backward so unnecessarily. And the last one in actuate, so the target lane offset gets converted into a S triggered steering tips and is sent as a float pair, steering and acceleration over the control socket back to the simulator. So among all, the important part is how these three stages talk to each other. So they share one common data structure. The shared data dictionary is protected by a trading lock. So this is a direct copy of the UCOS2 shared memory mutex pattern, where writers hold the lock only for the brief moment they're updating, and the readers at the same time grab a copy and release it immediately. So that keeps contention low, so a slow state never blocks the others. So now moving on to the next part. So we implemented the pipeline as 5 separate RT tasks. So from the table, first of all, the two cameras, one camera is the front one, another one is the back. It runs every 5 milliseconds at high priority because sensing has to be the most responsive. And then perception, which is the heavy vision work, runs every 20 milliseconds. And decision runs every 25 and send controls. And the last need acceleration, it runs every 10 milliseconds at high priority. Also, the periods actually follow rate monotonic ordering. And that means the tasks with the shortest periods get the highest priority. That's exactly what the UCOS2 model expects. Now, the key results on the right. So when we utilize all the five tasks, that's worst case execution time divided by its period. So we get a total CPU utilization of 53.3%. And the rate monotonic scalability bound for a five task already mentioned the previous slide is set to 74.3%. So we are comfortably below the ceiling, and our task set is probably scalable. Every task granted to meet the deadline. And the last thing worth mentioning here, the perception was by far the most expensive task because of the confused finding and the Euro interface. So we just didn't assume its timing. We also measured the worst case execution time live at runtime using a max execution field. It counter inside each RT task. So that's all from me. I'm forwarding to Yusuf.
Thank you, Arnold. So now we're going to talk about the challenges that we face throughout the development. The first challenge is the darkness, which means this HCV it's less than 24 triggers reverse acceleration for light recovery. Unknown tokens flagged as hazard, which like a value equals -7. That means avoid all tokens 4 seconds after the event clears. The second challenge is chasing car. Rear car motion differences plus a cyan color gates with hue 78 to 100, 104 isolate the car. The controller commits to a dodge for 1.1 second on a first detect, 0.8 second on a second. The third challenge is the police car. A dual color test, red more than 12%, and blue is more than 10% in one blob. Uniquely IDs the police car. A light bar detector fires early. Controller then hunts the nearest and token up to 10 per second. The fourth challenge is a golden line. A yellow banner detector scans the top to 20% of the frame. Sums green token mass per lane with an edge bias and counts the richest lane for 5.5 per second window. Okay, and now we are going to talk about the performance across the game phases. So currently we had like a 4 phases throughout the development. The first week we go into for distance is 39,000 per meter. We did test the speed and we did check the token and events, and this is only for the distance. No events happen. The second phase we implement the speed and the tokens and events. All the event pass with 30,000 meter, and the speed is 0.9. This was for token avoidance baseline. The third phase, we focus about the best challenge coverage, which the distance went to 30,000 meter and the speed 0.35 with the event all passed, and the tokens was focusing on and the green, like the green the most one 59, 59, and the red is 40 and the yellow is 39, which is like kind of bad because the difference between the green and red is very close and the speed is 0.35. But in the live, we did a great distance, 69% thousand with the speed 1.1, and the tokens, the difference between the green and red is very far, 64 versus 30 and the yellow 40. But we failed on the police and the golden line. This was the best live distance, as this is the best live distance, and the best challenge coverage was 13,000 meters. That's all I have, and you're going to jump to Danny.
Okay, thank you, Yusuf. The benchmarking versus RKJ. This slide compares our project with a real research paper from 2026 called Deadline Adhered Edge AI for Intelligent Vehicles. They used a real car with special hardware called Gaston Orion Nano. We used a normal PC with Python, but both projects use the same idea: perceive, decide, then actuate. So you can see the table compare many things. They used a strong AI model called YOLO V8 with a stereo camera. We used similar color detection with HSV. This task time is 10 to 100 milliseconds. Ours is faster, 5 to 25 milliseconds. Now look at the yellow box on the right. Uh, this is the key point in real paper. The math said their system should fail because the workload was too heavy, but in real testing, it worked fine for 423 day and night runs. This shows that in soft real-time system, the average time is more important than the worst case. Our project shows the same idea. Moving to the next slide. From simulation to physical vehicle. Now I will explain how we can move our project from a simulation to a real work and car. There are three main challenges we need to make. First, high-speed optimization. When the car drives faster than 100 kilometers per hour, we have less time to react. The steering time must drop from 80 milliseconds to 20. We can use a GPU for the AI part and move it to C++ for better speed. This will make the system more stable. The second thing is the lidar and radar fusion. A real car needs more sensors than just a camera. Lidar and help see in low light, and radar work in rain and fog. We add a new fusion task for over every 50 milliseconds to combine all the sensor data into one 3D map. The third thing is the real world schedulability. In our project, we count execution time with software, but for a real car, we need special tool like Absence AI to measure the worst case. We also need to test on real car hardware. Safety standard require less than 0.1% missed deadline. Moving to the last slide, the conclusion slide here, you can see we want to share the main point of our project. First, we built a 5-task design using the software Micron and our receive compute actuate pipeline run at 53.3% utilization, which is safe. The second thing is our architecture matches the real world. We use the same fixed priority task, YOLO V8 detection, and share Blackboard communication as the 2026 paper. The third is our system was proven in these phases. We got 30,861 meters on the leaderboard with all challenges passed. Our best left run was 69,185 meters at 1.10 times speed. Last, we have a clear path to real hardware. We just need to add the log-free data structure and hardware interpreter scheduling. Uh, uh, I think that's it. Thank you for listening to our presentation. We are happy to answer your question.